Now we come to a new concept called electric flux. Electric flux. Now flux looks like a threatening word, right? Flux. But it will not be so threatening if you understand it means nothing but flow. Also, this is not an invention of any physicist, rather, this is a word already being used in English. So, when you say influx of refugees, that means inflow. Okay? The influx of tourists, and the opposite of it is efflux, that is outflow, outgo. Okay, so flux is nothing but flow. Okay, so it sounds technical and it sounds a bit intimidating, but if it won't if you understand that it means flow. Now what is flow? Okay, we know that there is a fast flow and there is a slow flow. So how do I know what flow is, right? So the river flows leisurely or slowly. It means somehow we are referring to the velocity at which the river is flowing. But try to understand, if the velocity of flow is less, then for the same cross-sectional area, say the river is flowing like this, though it does not flow across such a regular cross-section, but still, for understanding sake, I am saying, so this is how the river is flowing. So say, hold on. So this is the cross section, and say this is how the flow is. Okay, say it is flowing like this, and I have cut it across. So this is the cross section. Fine. Now when I say that the velocity is less, I also mean that the volume is less, right? So flux here for flow of water we'll define as volume per unit time, and our time is second. So I actually mean it is volume per second. Okay. Now how do I calculate it? So let us try to understand. If say I have a cross-sectional area, I have a cross-sectional area like this. Okay, let it be A. Okay, let its area be A, or better still, the convention that we use in physics, let this area be S. Okay, so this is a window, a rectangular window, which looking like this is kind of showing to be, okay, so the flow is from this side. Okay, so it looks like a rhombus, but it is actually rectangular, and through this window, perpendicular to it, there is a flow. Okay, so this is a cross sectional window. So looking from this side, it looks something like this. Okay, this is the surface area, and and towards us, okay, towards us water is flowing. So what is the amount of water that is flowing out per second? If the velocity of flow is v meter per second, okay, if it is v meter per second, what is the volume flow? Now in 1 second, in 1 second, it comes out by an amount v. Do we see that? It comes out by an amount v. So this is the cross section. This is the cross section. Okay. Here, in 1 second, and assume that the water is say solidified for a moment. Okay. So it's flowing like an ice. So it flows out a length v meter in 1 second. Okay. And what is the cross sectional area of this? The cross sectional area will be S. So what is the volume that is coming out? It is a cuboid with cross sectional area S and a length V. So it comes, so the total volume is, so this total volume is equal to how much? Okay, that total volume becomes total volume is equal to S into V. Is it not? Because S into V is the volume of the cuboid per second. So it is S into V meter cube per second. Because it is volume, the standard unit is meter, standard unit of length is meter, so the standard unit of volume is meter cube, and this much amount has come out in 1 second. So the total volume that comes out is S into V meter cube per second, right? Now it is not essential that if there is a window, the velocity will be absolutely perpendicular to the plane of the window. So for the first time, we define our area to be a vector. Okay, this is for the first time that we are doing it. So we define the area, we define the area to be a vector. Now a vector has both a magnitude as well as a direction. So what do? So with magnitude equal to the magnitude of the vector is equal to the magnitude of, the area. Okay. Now direction is something that we'll get stuck in. Why? Because what should be the direction of the area? If I take it in the plane of the area, say like this, then there are infinite number of directions, right? We have infinite number of directions, and that will be a bit confusing. So what we do, we take it perpendicular to the area. We simply have no other option. Okay, so area and direction perpendicular to the plane of the area, perpendicular to the plane of the area. Okay, perpendicular to the plane of the area. Now there are two perpendiculars to a plane, no? So if this is the area, this sheet of paper is an area, then either I am talking about this perpendicular, or I am talking about this perpendicular. Which perpendicular? That you will understand, but currently we are taking that perpendicular in the direction of flow of the velocity. Fine? We are taking it in the direction of the flow of the velocity, so it becomes unique one. Okay? So we have defined this area to be a vector, and if I do that, then the area vector is something like this, shown by the red vector, and it is equal to S. Okay, it is equal to S vector. Now the total volume is equal to S into V, S into V. Fine. Now let us try to understand. In the same case, I'll erase this. Let us try to understand the case when the velocity vector is at an angle to the area vector. Okay? When velocity is at an angle to the area vector. When velocity vector is at an angle to the area vector. Currently, what was the angle here? Angle was 0 degree. Why? Because both of them were parallel, right? Now, when it is at an angle to this, let us try to draw the same thing. This is my S area, and the area vector was something like this, and the velocity vector is now at an angle theta to it. Now what happens? So what happens is this. This is my area vector. I have the red pen. This is my area. My red pen as the area vector. Okay. Red pen as the area vector, and the black pen at an angle like this, and this black pen is the velocity vector. Now this velocity vector has two components. One is v cos theta in this direction, another is v sin theta. So v cos theta is parallel to my area vector, that is perpendicular to the plane of the surface, and v sin theta is parallel to the plane of the surface. Correct? It's parallel to the plane of the surface. Now this v sin theta component, see, just like water moving on the face, it is not moving across the area, right? So the v sin theta component is simply not contributing anything to the flow across this area. Why? Because this, you see, You see, imagine this to be your window, and imagine raindrops falling absolutely perpendicular to it. So what happens? Nothing comes across this window inside the room, nothing goes across this window outside the room. Right? So what happens? It is only the v cos theta component which is leading to a flux across this area. Okay? There is a flow for this raindrop, but this is not across the area. It will not cross the area, right? So if it's just like this, then it just does not cross the area. Fine? So what I do is here the v cos theta component contributes to the flux, However, v sin theta component doesn't lead to a flow across the area S. Right? So what is the flux? Therefore flux is, now see, instead of, in 1 second, instead of v, as in this case, we have this hole with this cross sectional area, we'll have a v cos theta length in 1 unit time. So what is the total volume? This area S into v cos theta, right? So flux is S into v cos theta, right? Now I have this v velocity as a vector, S as a vector, and there is a cos theta term. It immediately tells me that this is v dot S. V dot S. Why? Because if I have A and B as two vectors which are co-initial, and theta is the smaller of the angle between the two, because why I say smaller? Because there is another angle which is this, but I am talking about that angle. So it is smaller of the angle between the two, then A dot B is given by AB cos theta. Okay? So it is V into S, V dot S, right? It is V dot S. Now just let us see, if this theta was 0, then cos 0 is 1, then this reduces for theta equal to 0 as S into V, which is this. Okay? So this can be considered to be the general term. This can be considered to be the general form for the flux of water across a cross-sectional area S. The way we have taken the area vector to be a vector, should be very well understood.